Take a look at this image. What do you see? Is it a beehive? Maybe it's a piece of fabric. Let's take a closer look. Now that might be a bit blurry, but what you are looking at are interconnected graphene atoms forming hexagonal structures. Yes, that's right, we can image the actual atoms. To get a sense of scale, these images are looking at objects that are over 70,000 times smaller than the width of a human hair. That's like comparing the size of a penny to the length of not one, but 14 total football fields. So, how do we go about capturing such images? Well, these particular images were captured using something called a scanning tunneling microscope, or STM. However, this device is no ordinary microscope. Unlike conventional microscopes which use light to observe a sample, this device relies on a simple yet clever design to measure things at an atomic level. To be more specific, an STM uses something called a tunneling current. This kind of electron current is the result of two conductors being brought really close together to a distance close to the size of an atom. At this distance, an interesting quantum mechanical effect begins to occur. First, let's picture the atoms of our two conducting materials as simple nuclei surrounded by electron clouds. These clouds represent the probability of finding an electron a certain distance away from the nucleus. When two objects are close together, all that separates these electron clouds is a small empty space that we call a vacuum. We can treat this vacuum as an energy barrier between the two materials. Classically, this would mean that the electrons cannot pass through unless they have a higher energy than the barrier. However, quantum mechanics tells us that if an electron tries to pass through the barrier, there is always a small probability that it tunnels through. After some math, we can find that this probability decreases exponentially, depending on the width of the barrier, which is the distance d between our two materials. This means that the tunneling current typically decreases by around 1 order of magnitude for every 0.2 nanometers of distance. Or put simply, any tiny changes in the distance will give us a big change in our tunneling current. So, how does an STM generate a tunneling current? Well, the design in theory is actually rather simple. In a nutshell, the STM uses a very sharp tip of conducting wire which is one or a few atoms wide. Then, all we need to do is bring the sharp tip close to the sample we wish to image. Then we apply a small voltage between the two, and this voltage will help us push the electrons towards the probe, which means we have a tunneling current which flows in one direction. Now that we know our current depends on distance from the surface, we need to control the movements of the tips and decide how we're going to use it to image our sample. To achieve this, the tip is placed on a small piezoelectric tube, which is made from a material that can change its shape based on an applied voltage. This allows us to control the tip's position with precision over very short distances. Then, to image a sample, we first need to decide how we're going to collect our data. In most STMs, there are two modes in which this is done: constant current and constant height. As the name suggests, in one mode you want to keep the tunneling current constant, which means that we have to move the STM tip up and down whenever the current changes, which means the position of the tip becomes a map of the surface. Meanwhile, in constant height mode, we simply keep the position of the probe at a set height. Then the changes on the current will indicate the changes on the surface topography. Finally, all that is left to do is to scan the probe over the sample in a zigzagging pattern. So this way we can map the whole area. Then we have our image. Now there are some caveats that we have to address. What I said before is by no means simple, so it's definitely not the complete picture. First, as you might know, temperature is the result of particles vibrating. So if you're doing measurements at the atomic scale, you have to make sure things are really cold. Secondly, since we need samples to be understood chemically by airflow, the sample and the tip have to be in a vacuum chamber. Third, making and maintaining the really small, super sharp sample, which is an atom wide, is quite difficult and sometimes considered a bit of a dark art. And fourth, getting the electronics to measure these incredibly small tunneling currents and control the position of a tip was really difficult at first. This is why the physicists Gerd Binning and Henrik Rohr, when they managed to develop a working prototype of an STM, it earned them the 1986 Nobel Prize.